Good morning. It is time for our session, session 5. I almost said session 3. This is our Paleo AMOC session. So just a little background in history. We joined the AMOC science team late. I actually was at the 2009 AMOC science team meeting in Miami as a fairly fresh PhD, just interested in learning more about this idea, this AMOC thing, coming from tropical climate and more interannual variability was more my interest, things like ENSO and low latitude processes. So I sort of was intellectually interested. And at some point, I showed up at a poster. It was about 2014. Then I showed up at a poster that Mike Patterson was standing in front of about AMOC science team activities. And he and I got chatting and talking about how paleo records really could answer some of the questions that this community was asking. And so he said, let's do a workshop. And that started off a 2015 workshop that tried to bring together modern and paleo AMOC communities. And we really learned that there were 4 communities. There's the modeling paleo, the observational paleo, the modern observations, and modern modeling. And we tried to all talk to each other. And I think that in the intervening years, we've through the AMOC science team activities, we've really come together as a community and forged some new collaborations. So I also wanted to acknowledge Al Wanamaker, who, when I was asked to think about leading this task team, I said, I want to do this with Al. So thank you, Al, for joining me in this adventure. And prior to this meeting, Gokhan actually asked those of us on the organizing committee, why don't you pull together a few slides summarizing your field over the last, say, decade-ish? And so that was to help him summarize his introductory slide talk. But I also wanted to sort of highlight what we've learned from the paleo world about AMOC. And I really broke it down into 2 slides, and one focusing on longer time scales, and I'm going to say, forgive me, because I have not gone deep time, because certainly there's been a lot of interesting research in that too, but more glacial, interglacial. That to me is deep time, because I tend to work in the last few centuries. And so then the other slide is focused on that. So what have we learned about AMOC? And I want to say this is my perspective, and in consultation with Al, and so maybe our perspective, and not necessarily it's biased by all of what I know and what I've learned. So take it with a grain of salt, but this is my perspective. So I feel like maybe 15 years ago, we started out with this basic conceptual model. We have Holocene AMOC, upper left. Oh, here, let's see if I can. Yeah, you see it, yeah. Holocene AMOC in the upper left, where we have, and this would also characterize sort of the time period, warm time period. Ooh, mouse goes all over the place. Warm time periods, also sort of during the last glacial period. This is Greenland ice temperature. We had these warm events, and we think that might also be the model for what happened then. Then we have our glacial maximum ocean, where AMOC was shallower, and the debate still rages over whether or not it was stronger or weaker or about the same. But certainly, I think we have established, I think, thanks in large part to Andreas Schmidner and many colleagues from the OC3 working group, Page's working group, that we've established it was definitely shallower, and we really don't know about strength. And then the other part of this conceptual model is Heinrich events, where large ice armadas occasionally, if you can. Hard to see here the gray bars. There are gray bars on that during these numbered H's right there. Those are gray bars that go all the way down, and represent ice-rafted debris invading the North Atlantic, so large ice outbursts, and that we think that that might have shut down AMOC during those time periods. So some things we've learned, I'm actually, since I'm on that Heinrich, we're going to say Heinrich events are not all the same. Those iceberg armadas maybe didn't always shut off AMOC, and that's something that's come to light in recent years. Another thing I think we've learned is that what I emphasized about the AMOC being definitely shallow, but one implication of that is that I think we have a greater appreciation for is that by shallowing AMOC, it no longer participates in the global MOC, and that's been some recent findings on the part of, we've got Lund et al., Sykes et al., and Nadeau and Jensen, 2020. So then another thing we're learning is, or one thing that I think some people have learned, I'm not sure I fully understand all the details here, but the idea that AMOC is really potential, the modeling of AMOC might be biased towards monostable states, and that idea comes from trying to model the deglaciation and finding that salinity stratification in the South Atlantic that actually connects also to this line of thought about the global MOC and the importance of the South Atlantic and the importance of the Southern Ocean in the MOC. So and the last thing I wanted to highlight on this was the recent findings highlighting that Pacific and Arctic sector might actually have more importance than we thought, both in deglaciation, as we came out of deglaciation, as well as potentially Heinrich events. And of course, it's also a major player in the modern, so that's something to be thinking about. Let's see if I can change slides. I didn't practice that. Come on, because this is not my field. I want to get onto the Holocene. Okay. Mouse with the arrow. Oh. She does have the magic touch. Okay, I found the mouse. Where is the mouse on the screen? Yeah, okay. Oh. It's her laptop. I think that's why. It's not mine. No? Okay. So now that I've talked too much, I want to sum up in 2 minutes. So I feel like I wanted to sum up what I think we've learned about recent AMOC behavior, recent being last few hundred years to 1,000 years-ish, 2,000 years. And I feel like we're making progress with trying to reconstruct past AMOC using various fingerprints. I think that's an active place of research and of controversy. We have some caveats. I think we've heard some caveats about subpolar gyre indexes yesterday, but also I think there's a lot of other records that contribute to trying to do this. And I just highlighted here on the right a paper by David Thornalley. He's been here this week, and I think that is he used the subsurface temperature and sortable silt to point out that there may be some merit in the idea that AMOC has slowed down in recent centuries. So that it comes to the second point there. Maybe it has slowed down in recent centuries. I think that's another thing that we're still working on. I think there's conflicting evidence from different locations that we need to hash out what different parts of the system we're doing at different times and how do they relate to each other. And then the fourth thing I wanted to mention was this still unresolved, in my mind, link of how does AMV and AMOC relate. We saw some talks on that earlier this week, and I think that we're still hashing that out. Red noise persistence versus dynamics, and NAO forcing, what happens, how does it work? And I think that's something we're sort of on the cusp of really digging in and getting some good understanding of. So I think some key messages. We really have this, what I would call an off-width problem. It's from rock climbing. It's a problem where your hand doesn't quite fit into a crack, but your whole body doesn't quite fit, and it's sort of an off-width. And I feel like decadal to centennial variability is an off-width problem. In understanding the both, which we've seen earlier this week, the mechanisms, but also in the paleo world with respect to our proxies and what they can tell us. So trying to, the deep ocean, for instance, often has problems with time control at the scale. So it's still a challenge, but I think it's an addressable challenge. We still need to really work on deconvolving the modern forced variability from the unforced variability and understanding that better, and that's where our long paleo records can really help. And I really want to emphasize this idea of the collaboration between modern and paleo folks being really key in solving these off-width problems. So with that, I want to start today's talks. Or actually, I'm going to turn it over to Al to start today's talks. Do you want to make the comment, or shall I, about, okay.
Good morning, everyone. I'm Al Wanamaker, Helly's sidekick. Before I introduce our first speaker, I just want to remind everyone of, let's make sure we're being constructive with our criticism. We're going to delve into some pretty controversial ideas, and let's just keep it positive. You know, that's going to be most helpful. So our first invited speaker for the paleo session is Paola Moffa-Sanchez, who will give a review of the paleo AMOC.
All right, Paola, do you want to share your screen? That works?
Yes, perfect.
Yep. And you can hear me, okay, perfect. Okay, well, good morning, everyone. I would firstly like to thank the organizers for thinking of me. This talk was the invitation to give this talk was a pleasant surprise after a really difficult year. So also I would like to say sorry that I'm not there. I'm actually sorry for myself that I'm not there in person, because I will miss all of the impromptu scientific discussions. So yeah, putting together this talk really took me back to 2010, the Bristol Rapid AMOC meeting, where I was a second-year PhD student, terrified of presenting some of my data in front of a lot of observational oceanographers and modelers. But after that, I realized how many exciting collaborations came out of that, and it was a really fruitful meeting. So before I start the talk, I would like to thank all my co-authors and collaborators, and really all the AMOC community, but also all the the Paleo AMOC community that have painstakingly put all of the records that I'll be showing together. It takes a lot of time, and I should probably say this before I move forward. It takes a lot of time to produce these records, and a lot of attention to detail. Okay, so today I will try to give an overview of what we've done. I will be mostly focusing on something that I've gained expertise on. But to start with, the first part will comprise giving an overview on how far we've gone over the last 20 years in terms of the progress we've made with some of the methods and some of the ways that we can look at the AMOC in the past. And then I will move on to giving some examples, although Ali has actually given quite a lot of those already, but I will give some examples of how these methods have been applied to understand past climate changes and the role of the AMOC on these. And then lastly, I will focus on the last millennia, mostly trying to understand centennial, multicentennial and multi-decadal variability and what have we learned from that. So, okay, so really just the motivation behind looking at past ocean. So here we've got an SST graph of the global SST, and you can see how the observations really don't go very far back in time. And so really by not having this later part, we're missing it makes it hard to separate. It makes it hard to understand natural variability, whether that's multi-decadal or centennial. Also makes it hard to separate what natural variability is and what anthropogenic influences have had on the climate system. That also, not having this part of the record also makes it really hard to reduce uncertainties when predicting future climate change. And so really what we want to be doing is improving some of this in order to constrain some of the models. So how do we do that? Well, actually, over the past, we've devised some really clever methods, and these have they've been increasing with time. And so here we can broadly look at two types of methods. Where can we find these signals? The first one is sedimentary archives, marine sediment cores, where sediment accumulates on the bottom of the ocean, and the organisms that live in either the surface or the seafloor also do accumulate with these sediments, and therefore we build up this record that unlocks some of the changes in the past. And here we've got a wide range of organisms that we can look at. We can look at the species composition of some of them, and we can also look at the chemistry, so the composition, the geochemical composition. We can also look at the sediment itself, the composition, the grain size, and that can tell us other things. We can and really what I wanted to highlight is what these archives can do. So sedimentary archives are really good because they give us a continuous record, but the temporal resolution tends to be lower. So now we've been able to push those boundaries, and we do have cores that maybe have a 2 or a 5 year resolution, but those are really hard to come by. Also, the dating is quite tricky. You get really large dating errors just because of the method that we use, and so that also becomes a problem. But the good thing is that these records can be continuous back in time, so we can go back millennia. The other good thing about these archives is that we can recover them from the open ocean. But now bear in mind that not every single bit of the ocean will have these high accumulation sediment cores. And so really what we want to, we only limit it to where this sediment is accumulating at high rates in order to look at the small details. So if we want to look at decadal centennial variability, there's only very few spots in the ocean that we can look at, that we can recover these sediments. Also, the good thing about these is that there's a lot of different proxies, lots of different organisms. You've got the sediment material, so we can do several measurements on the same sample, and that also gives us some idea of some of the biases that some of the organisms might be incorporating into some of the signals. But the other thing is we've got banded archives, and these are fairly new. So we've got either bivalves that live they've got long-lived bivalves. We also have deep sea corals, coralline algae, and tropical corals. And these are really useful because they put a layer of their shell every year. And so what it means is that every year we've got a record of how the ocean has changed. They're annually resolved, of course, and you can put these together just as if you were using barcodes with these growth increments. You can put them together, and I think the maximum has been going back 1,000 years. I think it's Dave Brennell's record, but I could be wrong. The other good thing is that they're absolutely dated because you count the layers, and so there's no error in those dates. However, these have an uneven distribution, and just because the animals have some preference, environmental preference, and they tend to be concentrated in shelf areas or the tropics, and so the distribution is not like the sediment archives, but you can get a higher level of detail. And here I've put a few of the chemical tools that we can use on some of these archives. Okay, so these archives give you a point in time and at their location, and then you slowly build up the record. And I just wanted to show this graph, this diagram, because I just wanted to highlight how difficult reconstructing past AMOC is when you only have a few limited areas and regions where you can, a few limited locations where you can go to. Here in the observational era, you've got all these array of moorings, and we might only get just a few points in the map, but also a few depths that we can get to. For instance, intermediate depths are really hard to get to unless you've got cores that are lying on these slopes. I just wanted to highlight this before we move forward. That is very hard to get at this complex 3D dynamic process that the AMOC is. But we can do something, so which is better than nothing. But no, we can do something. I'm actually confident that we're going to be pushing the field forward, and we're going to get to creative ways of getting at the problem. So what can we learn from these records to study past AMOC? So there's 3 broad ways that we can look at this. The first one is looking at the past changes in the ocean properties. So we can focus on like a location, or put several locations together and focus on the different AMOC branches. And we can reconstruct temperature, salinity, nutrients, sea ice, drift ice. Drift ice is actually particularly useful because it can also be dynamic, whereas the drift ice coming from, we can also observe that primary productivity. And also when we have locations that lie on fronts, then that's also quite a dynamic way of thinking about reconstructing ocean circulation. And it's true that increasingly we've worked with climate models, so trying to interpret some of this data with climate model results. And so really just to try and understand the processes behind the Paleo data in a physics-based model. And so we do these comparisons. I haven't put any references in here because there would be too many studies that have done that. Another way that we can look at the AMOC is by looking at the surface fingerprints, and particularly the temperature. And David Thornalley did this really well in his Nature paper. The third thing that we can do is that there's some proxies that actually already tell us about some of the dynamic processes, and some of them have already been mentioned. And so we've got these whole basin overturning proxies. We also have the reconstruction of the speed of the bottom, so the bottom flow speed of some of these currents. Also, we can use fingerprint of the water masses, either because of nutrients or where they originate from, and we can map out in the past the geometries of things like North Atlantic deep water versus Antarctic bottom water, also polar mode water, so we get further towards the recent. We also can look at ventilation, so looking at radiocarbon. That's another way of looking at the dynamics of the ocean by reconstructing how ventilated some of these water masses were. And then lastly, there's also been work done combining some of these ocean properties to calculate ocean dynamics. And there's really nice work looking at Gulf Stream transport, calculating the transport based on geostrophy, looking at the density in the Florida Straits across the Gulf Stream. So there's all these ways that we can use to look at the AMOC. So not only we've increased the methods that we can apply, we've also combined this to look at the AMOC, but also we've increased the number of records that we have. And this is just a very clear example. And I've only done this for the last records for the last 2,000 years. So here we've got 20 years ago. These are the records that were available. The greys didn't meet the criteria. The criteria really was 4 dating points for the time series, a length of at least 150 years, an average resolution of 100 years or better. And here we only have very few records that would meet that criteria. Marine records to date, as you can see, there are a lot more. And so this is actually really encouraging in order to get a better picture of what's happening. So what we can also something that we need to point out is that there's an uneven distribution of the records. You can see that they're clustered. That doesn't help when it comes to interpreting, but again, this is limited on where we can find our archives, as I mentioned before. There's also a large concentration in coastal shelf regions, and this also complicates it further to compare to let's say last millennium runs, where the coastal areas are not simulated very well. Then we've got disparities in the resolution, so some records will be really high resolution, some others will be lower resolution, which makes it hard to compare, especially with the age uncertainties. And this is one of the key problems, really, is that there's insufficient overlap with ocean observations. I think the dream job for any oceanographer is to get a record that overlaps the instrumental record, that overlaps the instrumental era, and extends back in time. And so this is something that we all look forward to working with, and actually the field will move forward as we push these boundaries. Okay, so just to recap the progress in the last few decades, we've increased the number of high quality archives, the temporal resolution, we've got better proxies, more quantitative, more data, so we've got more locations, so better spatial coverage. And then also with the advances, computational advances, that has also allowed us to have an interpretation of the ocean dynamics. Okay, so now I'm just going to move to the second part, which is how have we applied these methods in order to understand past climate variability and the role of the AMOC in this. So Hallie has also done a really nice introduction, so I might just skip through this quite quickly, but I guess what I wanted to say is that it will come as no surprise to everyone that a lot of the big climate changes and also more recent climate changes, the AMOC has actually either been actively or passively involved in some way or another. So here we've got an oxygen isotope record from Greenland, from a Greenland ice core, which tells us something about temperature. And we have this classic interglacial glacial sawtooth pattern, where we see really big changes in the temperatures, and this is already one thing. And then we can look into the abrupt climate variability that happened during the last glacial, which also probably happened in other glacials. And finally, I will really focus on this last part. Sorry, so modern is here, 0 is today, in the last part, which is our current interglacial. So glacial interglacial changes are, these temperature changes were coupled with CO2 changes, about 100 ppmv. And so the idea is that the ocean obviously has a massive carbon storage, and so it's probably the suspect for storing some of this CO2 between a glacial and an interglacial. And so the mechanisms by mapping out these water masses, as I mentioned before, so there's been a lot of work done on that. And I think the conclusion, and Hallie already spoke a little bit about this, so is that you get a shallower formation. So you get this glacial North Atlantic intermediate water formation in the North Atlantic with more influence of the southern sourced water. So basically the geometry of these water masses is changing in the Atlantic basin, and compared to what we would have today. And this has implications in carbon storage, just because there was a lot of sea ice around Southern Ocean, so less ventilation of these high CO2 waters, but also there was a big volume of Antarctic bottom water, which probably also held CO2. However, this is not the only explanation for glacial interglacial CO2 changes, and there's plenty more. There's plenty more explanations for this. So that alone don't account for this. So there's always ways where you can account for the different changes in the CO2. Hallie has actually talked about this, and I guess I'm not going to really go into much more detail. Just say that Heinrich events are still interesting to look at. So this is abrupt climate variability during the last glacial. They're really hard to it's still an active area of research. Some people considered it to be a prime example of this bistobal regime of the AMOC bistomal, but actually what we don't really know is whether is the fresh water that caused the changes in the AMOC, or if it was something else. There's more and more evidence that the fresh water came after the changes in the ocean already began. So although it did probably shut off, and not in all of them, perhaps it was a response as opposed to the fresh water responding as opposed to forcing. So now I'm going to move to something that I know more about, which is our current interglacial. So our current interglacial is called the Holocene, and this is again zooming into the temperatures from Greenland, and you can see that classically it's defined from 11,000 years, but actually until you don't get to 8,000 years, the temperatures didn't get stable. This is because you still have melting of the ice sheets and sea level changes. However, once you get here, there's millennial scale variability, but there's also centennial scale variability. This period has been classically understudied, and it's been understudied because the variability was probably too small, and the tools probably didn't allow to look at this period in much detail, but also because there were no records that were able to record this with the resolution that was needed. And so the AMOC again has been central to this, or it's thought to have been central to this, and really just as a potential explanation of Holocene climate variability, which can either be millennial or centennial. So we've got some forcing, so changes in the solar output, and volcanism, which would probably be very important for centennial variability. Then we've got more gradual changes like CO2, methane, and insolation due to changes in precession, so the way that the axis of the Earth is pointing around the sun for every season. And what you can see here is that in the early Holocene, the high northern latitudes received more insolation than, let's say, during the late Holocene. However, these forcings are really just not enough. These radiative forcings are not enough to see what we are recording in some of the records. And so the cryosphere, the ocean, and the atmosphere have normally been put forward. In particular, the AMOC has been central to this, either from fresh water coming from the Arctic or due to changes in atmospheric circulation. Okay, so just looking at the long-term Holocene evolution, and I'm aware that David Thornalley is going to be talking about this in a little while, so I might just go quite quickly, but I just wanted to highlight what we know and what we don't know. So the long-term evolution of the AMOC is still a matter of much debate, and I think he's going to shed some light with some new data on this. But what we can see is that by looking at different proxies from the deep ocean, we have found out that there are diverging trends in some of these deep AMOC branches. However, when you look a bit closely at the Iceland-Scotland overflow, it seems like it weakened over the Holocene, and you can see these in these two arrows over here. This also agrees with some data compilation where they use the principal component analysis, and they came up with an AMOC index, and it looks really similar to this ISO. So it could potentially indicate that, yeah, the AMOC had a structure. But then we've got proxies such as Protactinium thorium, which really do give us an idea of overturning circulation. And these two studies just highlighted how stable the AMOC was during the Holocene by using this proxy that can tell us something about the overturning. So as you can see, there's still a lot of contrasting results from the proxy records. The models are also not in agreement. There's a lot more model studies than I've shown here, but they show discrepancies in this long-term evolution. Although it looks like the high-resolution models may be showing a weakening also of the AMOC, but there's still differences across the models. So if we move to centennial variability, which is something that I've dedicated a lot of my career to, trying to understand whether the climate variability recorded in these high resolution archives was actually a result of changes in the AMOC. So here we've got, and it's not only that we've got these high resolution archives, but we also have documentary evidence. And classically, the last millennia have been divided into cold and warmer than average periods. So we've got, for instance, here the Little Ice Age, the medieval warm period, Cold Ages dark period, and the Roman warm period. And there's a lot of literature with regards to this, the centennial variability. And around the 2000s, there was a lot of work produced that suggested that indeed some of these centennial changes were found in the ocean, and changes in the overturning, or changes in the formation of the deep waters were responsible for these. However, these studies didn't have the enough resolution to try and look at these centennial scale changes in detail. And so since then, there's been a huge improvement in the records that we have, and also in the resolution that we have, and we've been able to look at these in a bit more detail, particularly focusing on the last millennia. So here we've got some of the records that we synthesized for the review paper in the special issue. And by the way, thanks to all the co-authors. This was a really huge collaborative project, putting all of this together. And so here we distinguish between water masses, and what we know is that there was lots of differences across the records. There were regions, for instance, over here, that we think that there was interaction between slope waters. Gulf Stream complicated some of the interpretation for these proxies. Again, here in this area, there was also contrasting different proxy records. It was very different when we got to the Atlantic inflow records that really showed this consistent millennial cooling, with some step-like changes when it got to the Little Ice Age and even before that, which are quite consistent across records. And I'm just going to divert slightly from this, just because I wanted to give an example of how we can improve. So here I've got some records that unpublished, and basically we looked at the same thing, so same proxy, across different sites, all quite high resolution. This is the temperature data across the last 2,000 years. What we were able to do is calculate the uncertainties in age and also in the temperature, and come up with these consensus analysis. I will work with statisticians in Finland to try and put this together. And once we did that, then you can see how the coherence, some of these records is actually quite good. The millennial cooling is present. You've got these step-like changes also present in these records. So I just wanted to highlight that perhaps what we're doing is that we're comparing apples with pears, and we're not quite getting the same answer from these two records. After that slow diversion, I just wanted to mention that we also find really consistent results from the East Greenland current. We see this cooling across the last 2,000 years, and it's consistent throughout. There's more ice-laden waters around Greenland, so over here, and we see more sea ice, more drift ice, and cooler waters, and with some step-like changes, again, when we get to the Little Ice Age and sometimes earlier. So it looks like we're getting these consistent pictures also in the East Greenland current. Okay, what can that tell us about surface circulation? So really what we think is happening here is that, and this has been, we were not the first ones to propose this, but of course there's an increase in drift ice and sea ice and fresh water coming into the subpolar North Atlantic during these cold periods. What is forcing this? We're not quite sure, whether it's internal variability within the Arctic. So we've got some sort of a feedback that every so often kicks in, and then you've got this dumping of fresh water in the subpolar gyre, which weakens the gyre, perhaps Labrador sea water, not entirely sure, and I'll say in a second why. Weakens the gyre, weakens the transport of warm waters and the heat northwards into Northwest Europe. And so and it's not just the data, so this is based on some of this data and the data I've just presented, but also the models agree with this, that with changes in the subpolar gyre alone, we could be looking at the really harsh winters that were recorded, let's say, during the Little Ice Age. And so this mechanism is actually really picking up. We don't need we think nothing is happening to the overturning, and I'll show you why in a second. But perhaps it's just the gyre recirculation of these waters that is having an impact on the climate of Western Europe. So what was the trigger? These are really outstanding questions. What was the trigger? Was external forcing, either solar or volcanism, internal dynamics? The role of the atmosphere, is the North Atlantic oscillation more important than the East Atlantic pattern? And was the AMOC affected by these cold periods? Am I still going?
You're good. We just lost the projector, but you're good for the online folks. I think if you want to keep going, and then we'll fix the projector as you're going.
Oh, okay. So, right, okay. So I just want to show some of the deep AMOC branches, and how, so these are some of the deep overflows and the western boundary current, and I've just put these together. Actually, we put this together for the synthesis paper, and just wanted to show how diverse the results are. Although I'm guessing people in the audience cannot see anything.
We can see it now.
Yeah, okay, perfect. I guess just the point I wanted to make is that the different deep proxies don't really show a consistent picture across the centennial variability. And also, if we start looking at the most recent period, so here, just trying to move towards the most recent, it does look like some of the records show some slower flow speeds, but it's not absolutely clear because we're missing really the top. So we don't really, it's really hard to get a coherent picture, but it looks like it didn't change much during these centennial scale changes. Okay, I just wanted to show this, not because I feel strongly about it at all, but I just wanted to show how much variation in the data we have. So this is sea surface temperatures between the recent and the pre-industrial. So basically, warmer means that the warmer is in red. It means that the industrial was warmer than the pre-industrial. And so what you can see is that there's a huge variability across the data sets. And if we try to look at either the changes between the northwest and the northeast, if we try to look for fingerprint patterns, it's not clear either that there were some coherent changes in this. There's a lot of caveats though, because maybe it's there, but we cannot see it because we're comparing lots of different things. And also we don't have enough data points for the last 200 years. And also we're looking at sea surface temperature records, which are normally very noisy because they're in contact with the atmosphere, and also they're very seasonally biased. So I think my conclusion from what we know is that there's not enough evidence from pollution-graphic records for recent AMOC slowdown, but we really need more high-resolution pollution-graphic data from the recent centuries. And I think maybe there's already some data underway that hasn't been published that I'm unaware of. But this is something that I just wanted to highlight. So just to conclude on some thoughts, so we have made some progress in understanding North Atlantic circulation changes, and that's thanks to a load of things like the proxies and models, the high quality of the archives. Coupling the data with the models has allowed us to get an understanding of the ocean dynamics, particularly at centennial timescales. And there's a consistent picture emerging for North Atlantic surface circulation changes that explain the centennial climate variability without having to invoke for whole overturning circulation. There's still some disparities across data and model and some challenges there. Okay, so moving forward, perhaps we should try to understand these disparities across the records. So what is each proxy telling us? And this is really not trivial. There's a lot of work going into this. Exploit, and I think this is really important, exploit and design statistical methods that can assemble data So not just looking at the wiggles and seeing how good they look between them, but also trying to account for their uncertainties and trying to put them together in a robust way. And also seeking original avenues to combine these proxy records so we can gain some insights into ocean dynamic processes. I'm not sure how I did for time there, but thank you very much for listening.
Thank you, Paola. I think for timing, we should probably move on to our next speaker.
Right, so we'll pick this up at the afternoon discussion.
So my name is Feng. I'm from University of Wisconsin, and my longtime collaborator Peter Clark and I did this work. Good. So it appears that the intuitive idea of freshwater forcing of AMOC had not been tested against the data because the modern AMOC records are short. And in the last few days, we know the modern AMOC changes are still in hot debate. That's why, so two of the biggest advantage of, much better, paleoclimate record is long record and large signal. Yeah, I know you also have a long record of hearing this, so bear with me. So here, the record is 5,700 year long. That's early Holocene freshwater flux. And the signal is 50 meters of sea level rise. So that's a lot of fresh water. I mean, David also showed the size of a Laurentide ice sheet associated with this freshwater flux. And you can see Holocene is very, very sneaky. Get 50 meter sea level rise, the AMOC did not change. And instead, actually, it's increasing. Also, the Greenland temperature also don't show any abrupt change that could be associated AMOC change if there is AMOC change. I mean, besides there are a little bit 9.2 K events, 8.2 K events, bomb cycle. Paola had already showed that in her previous talk. So I know you are trying to get throw jobs, and so I did it for you here. So 50 meter sea level rise is about, in 5,700 years, it's about, actually, it's covered, 0.1 throw job. And then the Bering Strait also opened, so the freshwater from Pacific flooded the Arctic gradually. So that's 0.08 throw job. So basically, a total freshwater flood into Arctic, North Atlantic in the early Holocene is about 0.1 to 0.18 throw job. So basically, that's a problem, right? So basically, I just read this. We call this Holocene meltwater AMOC paradox, HMAP. So basically, AMOC sensitivity to freshwater input change is shown to be muted. We don't know why. When freshwater flux associated the final northern hemisphere deglaciation considered. Actually, this is almost the same slide for my prelim. I told my PhD committee 15 years ago, there's no way I can put in 0.1, 0.18 throughout of freshwater into Atlantic, and the AMOC can still be up, and the Greenland temperature can still warm. And my committee was impressed and signed my prelim, then just ignore the whole thing. And that's what I get, This is the cyan curve is from my PhD dissertation. So you can see, you put in freshwater there. So the black curve actually is data reconstruction. The cyan is, we call it trace 21K1. So that's actually pretty influential. A lot of people are using that because it's easy to compare proxy data, right, with time series and time series. So you put in fresh water, so top curve AMOC, the AMOC was down. I mean, obviously, to me. Then the Greenland temperature is colder in the early Holocene. Then the Mediterranean SST, you know, the remote effect, also colder than the observation, much colder than the observation. And Antarctic temperature actually is warmer than observation because the heat stopped going to the north. And it's a little bit embarrassing that for me to see that it took me 15 years to fix this problem. That's the red curve. So basically, if I basically assume what we learned from the data, the muted response of fresh water to AMOC, so basically I just don't put in fresh water. And that's the red curve. And it has much better agreement, at least to my eyes. So basically, the AMOC is up. The Greenland temperature agrees with Greenland reconstruction, one of the best temperature record. And then the Mediterranean SST from 8 SST record, basically it's a stat. And then the Antarctic temperature shows it's colder because AMOC is up. I think, by the way, it's quite impressive for a modeler to see this. You know, you get a model, don't change anything, then you put in your AMOC, put in CO2, your ice sheet, and the orbital force, and then you can reproduce the record from ice core, not only in one location, two locations, then also sea surface temperature in the Mediterranean. I mean, that's magic. I mean, right or wrong, I don't care. It's really magic. Then the question for you guys, so you don't ask me questions. Can we prescribe AMOC in the model without using freshwater forcing? I know you guys don't like that, but the AMOC, so, you know, for yourself, we need heat flux for the climate simulation. So I don't care AMOC, I only care heat flux. And I don't want freshwater flux for AMOC. So just give me a way so we can all do a better simulation. And then, so summary, both the model and data support that freshwater forcing of AMOC is muted. It's another way of saying that if you want to reject this idea, you have to reject both the data and the model. And then the question is, what's causing the bias of high sensitivity of AMOC to fresh water in the model? I really don't know. But one thing I know, this is for Leeds. It's not due to model resolution. So basically, people have done that. 1/6 ocean model, you know, put in fresh water, it goes along the coast, you know, coast trap currents. And then the AMOC shut down, like not shut down, decreased by about 1/3. And then another study, modern by the fantastic study by Laura Jackson, basically showed the 1/4 degree RTCC model have a deeper reduction of AMOC for global warming than the 1 degree couple model. And then Wilbur, wonderful study. So basically said it, spatial resolution in itself does not impact AMOC sensitivity to radiative forcing. So okay, the implication of Holocene meltwater AMOC paradox for future projection. So basically that's the last half sentence. So AMOC may not be as sensitive to freshwater flux and the Arctic freshening as is currently projected for the end of the 21st century. I know you don't like this. So that's the reduction we get from RTCC model. But my question is, a semi-projected AMOC decline in 2100, partly or predominantly due to Arctic sea ice melting, plus the, you know, P-, river runoff. But here I focus on the Arctic sea ice. Because both semi-fine models, so wonderful study from CCSM4, basically said, in the lava sea, the surface freshening is caused by strongly increased liquid freshwater export from the Arctic. And then if you ask Gaurav Madan yesterday at his poster, he will tell you 15 CMX6 models, the AMOC decline is due to sea ice melting, flooding the whole subpolar gyre. So here we go. How do we kind of get away from this Holocene meltwater AMOC paradox in modeling, in AMOC modeling. We can follow the CO2 protocol. You know, our common cycle model is still in its infancy, so basically not good. So, but we still do a lot of good simulation with CO2, right? So prescribe CO2 for climate simulation of past and future. So even though we don't know the carbon uptake by the ocean, we can still do future projection. That's amazing. Then we can also treat the treat any predicted CO2 changes from carbon cycle model with caution. So if I replace CO2 with AMOC, that's my final slide. If you are concerned with this freshwater AMOC paradox, prescribe AMOC for climate simulation of past and future, and treat any predicted AMOC changes from climate models with caution. Thank you.
Okay, thank you, Feng. One quick question, and then we'll head to break and posters. Okay. Chris, you're going to have to catch him out at the coffee place.
This is Ali Siddiqui from Johns Hopkins. I guess just a simple question, which I guess everyone's going to be thinking about. Why do we not see sensitivity of the AMOC to this freshwater forcing?
Yeah, that's why I came to this conference. Sorry, I don't know.
Okay, that was quick, Chris. You get to go. Okay.
I think this is basically just asking the same question, but I mean, what is fundamentally different about sea ice, freshwater fluxes than land ice in terms of, is it that?
Land ice, you can get away, just don't put it in. So common cycle, no, actually model, yeah, don't put fresh water in the ocean. Sea ice, so there's a question for Gokhan. Can you get global warming? Actually, that's a separate question. So basically, can you actually don't let the melting of fresh water from sea ice into the ocean? I know it's melting, but so basically we have an AMOC model instead of common cycle model here. So our AMOC model is freshwater forcing of AMOC. It's not working. It's like a common cycle model. It's not working. So how do we fix our AMOC model? So so basically we ignore this AMOC model. AMOC is hugely important, like CO2 for climate projection, past climate simulation. We just assume our AMOC is basically what coded in the model is working. It has not been tested.
Okay, we're going to say one more thanks to the morning speakers and meet out in the atrium for a break and post.
People online also know that it's time to get started. I hope you all had a good and stimulating discussion during this break and poster session. Welcome back. And I want to, I guess, first just introduce the first speaker, Yvan Romé from the University of Leeds, and he'll be speaking to us about mechanisms behind climate oscillations in full glacial simulations. So thank you, and Yvan, share your screen and we're ready to go. Oh, we don't hear you. You're not muted.
Yvonne, we do not hear you right now.
I'm gonna.
Or did a test with them. Sam, are you able to request to unmute him?
Oh, that's right.
Not muted? And the audio? Bokon's wondering if you can take off your microphone and see if it helps. Unplug it. Don't see him on my call. He's not moving anymore.
I'm gonna just check 1, 2.
Should we move on to the next speaker then, and we can come back? Yep. So let me set this up first.
See it now.
Well,
We don't see your face.
well, that would be okay. We'll do that. So yeah, I was going to start the talk by saying that I was very sad not to be able to be with you today. It's even more true now because obviously it was much easier in terms of presenting that. But I'm very grateful of the opportunity to be able to present these results with you today because I have presented these results in the Paleo community, but feel like some of the concepts I am using there actually are at the crossroads between the Paleo and the more modern oceanography community, and that sometimes we probably don't have the skills to look at that within the group, and that any input, advice, that I could get on that would be very helpful for the rest of the project. So those results are based on the first 2 chapters of my PhD that I'm doing at the University of Leeds with Yvan and Valentin, which started as a study of the last deglaciation. So we just were trying to produce transient simulations of the last deglaciation. But when you get to the last deglaciation, you do have these Bowling, Adderode, and Younger Dryas oscillation that echoes to the climate oscillations that happened during the last glacial period that have been introduced in the previous talks, Dansgaard events, where the climate oscillated between cold and warm climates, and that it is necessary basically to be able to reconstruct the last deglaciation to understand why we saw this oscillation at the time. And even if the mechanisms are not understood fully understood behind DO events, there are no clear links with changes in AMOC modes that already also have been introduced in previous talks. I'll go very quickly on them, just saying that in order to study the mechanisms, we need to be able to reproduce AMOC mode switches in climate models. And that has been an effort from the scientific community for the past 10 years and has proven to be very challenging to reproduce them, or at least in glacial condition. And I'll give the example of Marlena Kluckmann's work that she did with the MPI model in Germany, where she did manage to, by tweaking the parameters, obtain very nice AMOC and climate oscillations, but never using LGMI sheets. So as I said, for us, we started as transient simulations of the last deglaciation, and we were very lucky actually to obtain oscillations, but we were not looking for them, but we were very lucky, and then we decided that instead of continuing this transient approach, we should take the opportunity to study these climate oscillations in glacial backgrounds and try to exhibit the mechanisms that are behind these AMOC mode switches. And I suppose we also wanted to use a slightly different approach to what we usually see in the literature, which is that like a lot of AMOC stability discussions, at least in the Paleo context, are done by looking at that in the forcing space, and basically by studying variation in the forcing can trigger a different AMOC response, whether it is forcing it in a cold mode, in a warm mode or in between, where we have like this window of opportunity where the AMOC can oscillate between warm and cold modes. So that's something that is starting to be well studied, but I was more interested in trying to understand, for specific forcing, what is the temporal evolution of the AMOC and what is the dynamics, and basically understand what was the combination of the more stochastic part of the dynamics, where the AMOC will oscillate in a stochastic way, and it's something that has been discussed in previous paper, and the more deterministic dynamics, which, for example, the theory of the salt oscillator, where the AMOC oscillations would be very regular, and actually would be the changes in the forcings that will introduce the irregularities that we see in the records. So that leads me to presenting some sort of like our theoretical idea of AMOC changes that just relies on the theoretical view of potential, and then trying to see the AMOC modes as stable states in potential wells, and then to try to understand how the fast physics, the fast components of the stochastic dynamics can help the climate system to switch from one stable state to another by overcoming energy gaps that are created by the potential, or if stochastic dynamics itself is not enough to switch to a different state, how can the slow component of the more deterministic dynamics can change the shape of the potential and therefore promote or prevent switching from one mode to another. So that's the sort of theoretical framework that we wanted to sort of illustrate with our simulations that I'm going to present now. So these simulations, they were realized with ATCM3, which has a 1.25 times 1.25 resolution over the ocean. When we started from simulations of the last glacial maximum at 21,000 years ago, to which we added meltwater discharge derived from the last glaciation history of an ice sheet reconstruction. But as I said, because I was more interested in looking at one specific forcing, instead of using the transient history of the freshwater forcing, we decided to select 6 snapshots that were representing different sort of distributions of meltwater in the North Atlantic. And then we used these 6 snapshots of meltwater forcings as fixed forcings for the 10,000 years of our simulations. And among these 6 simulations, 3 of them showed very nice oscillations. That's why the one I'm going to present now. So during these oscillations, what we see is that we go from, after a transition period over the first 2 cycles, I would say, we see a clear cycle going from a cold mode, where the AMOC is pushed very back, very south, to a meridional mode first, so like one first warm mode, where the deep water formation sites are primarily located in the Nordic seas and the Iceland Basin, before switching to another warm mode, which we call the zonal mode, where the convection in the Nordic seas is shut off, and the convection will resume in the Iodegan Sea and the Labrador Sea. So instead of seeing that as a 2 wells potential, I suppose now our idea was like trying to find different variables that would help us to see that as a 3 wells potential. So here like in 10 minutes, I don't have time to go through all the results and all the tests we've done on different things. But just to give an overview of what we're looking for, is that we're looking for sort of variables that can be translated into energy, and then that would show like such like during the stable modes and gaps during the transitions. And for example, looking at the salinity fluxes in the Arctic region, we do see that we can exhibit like three stable states and gaps between the cold and the warm modes. But that in itself, the salinity in the Arctic wouldn't be able to explain why we have transitions between the two warm modes and why the cycle would go in one way and not in the other. So this is work in progress, and we're trying quite a lot of different components to see if we can have, to see what sort of variables we should add to potential to try to make it fit the vision that we had. And basically that's where I'm asking for any input advice from the community that has been more used to look at like different sort of variability within the AMOC, and that could be used to explain the variability we're seeing there. And the way we relies on slow physics, where we sort of observed, for example, differences in density and salinity gradients, whether it is on a meridional scale or a vertical scale, that could explain why the shifts happen after a certain amount of time, but also in the fast physics and the stochastic variability, where even if we don't see major changes in the internal variability, we sort of see some of like decadal and centennial events that could be drivers of AMOC mode switches. So that will be all for me. And I just have my contact in case anyone had any comment on that I wanted to share. I'm happy to take any questions you may have.
Thank you, Yvan. Any questions? Tom?
Just a brief question. It looks from your last figure that you showed as if everything is happening in the North Atlantic and nothing the Nordic seas are not involved. Is that correct?
On this one, you mean?
Yes, correct. Yeah, you don't go into the Nordic seas in your latitude there.
So no, yes, it is a good remark actually. So we do see changes all over the North Atlantic, and then here we're just only interested in. So like what I'm showing here actually is what I call the center of mass of the MLD, and it should be not taken as where the convection is happening, but more a way to move in a state space and to observe different states. But on the thing in the Nordic seas, we do see changes in salinity and density in the Nordic seas, but actually the center point would be the Iceland basin and how the convection sort of transition around that, and what salinity reorganization it implies. So I don't know if I understood the question well. If it was about the scale doesn't represent where the convection happens, but more a global idea of the organization of the convection.
We have time for one more, if there's one. I think we'll move on. Thank you very much, Yvan.
Stop sharing my screen. Thank you.
Yes, so we have Shantong now.
Yeah.
We'll get you up. Yep, we see you now.
Okay, great.
And just share screen, and I think we'll be good to go.
You see it?
Yep, so hold on, let me just actually introduce. So Shantong is from Caltech, and we'll be talking about interbasin redistribution of heat and nutrients due to AMOC changes.
Thanks
You're
for
on.
the introduction. Thanks. Okay, so in the last 2 days, our meeting has been focused primarily on the Atlantic and South Atlantic basin. So in this talk, hopefully I'm going to shift your attention slightly to some other remote places like in the Pacific and Southern Ocean. This talk, I'm going to introduce some interbasin return responses and talk about the heat redistribution. Hopefully I can convince you that when AMOC weakens, there will be a compensating overturning occurrence in the Pacific that is associated with heat redistribution, as well as the nutrients redistribution. And I have included my email on the website there, so you can reach out to me if you are interested. So this is a shortened version from a long talk, so I skip a lot of details. If there's anything that's not clear, feel free to ask a question or reach out to me later. Because this is a Paleo session, I'll start from this record. This is an ice core record. This is a composite of ice core record during the denser ocean events. Blue line showing the Greenland ice core record for temperature changes, and the orange line showing Antarctic temperature changes. So you can see that following the abrupt warming temperature increase in Greenland after a couple hundred years, Antarctic is showing a gradual temperature decrease, on millennial timescales. So this antiphasing temperature changes between Greenland and Antarctic has been attributed to changes in the Atlantic overturning circulation changes. So on the top right-hand side, I'm showing the diagonal heat transport by each basin. And you can really see that Atlantic stands out there as purple line because it has a northward heat transport throughout the latitude of Atlantic basin. And has been, postulated as a bipolar seesaw paradigm like here. So when AMOC, it's assuming that when AMOC weakens, there will be a southward heat transport that eventually goes into the Southern Ocean, causing such a bipolar antiphasing temperature changes, and also assuming Southern Ocean as a heat reservoir, such as to account for the more gradual changes in Antarctic. However, we know that the climate response to AMOC changes are not confined to the Atlantic and Southern Ocean. Here I include a figure from, a figure from Pedro et al. 2018, showing the meridional heat transport responses after the AMOC collapse in their CSM3 simulations. And the red line showing the meridional heat transport responses following an AMOC collapse in the Atlantic basin. And we see that when AMOC collapses, it will be a southward heat transport anomaly. And most importantly, the part I want to draw attention to is mainly in the southern hemisphere, especially close to 30 south as the southern boundary. And with the southward heat transport in the Atlantic basin, in the Pacific, there's a northward heat transport anomaly that compensates the Atlantic. And when we sum them together, the meridional heat transport responses by the global ocean into the Southern Ocean is pretty small. This residual is much smaller compared to either Atlantic heat transport or the Indo-Pacific heat transport. And I'm going to attribute this interbasin heat transport responses to interbasin overturning responses here using this schematic. In the background, I'm showing the temperature from, I think this is the echo, if I remember correctly, in the Atlantic basin, in the Pacific and Southern Ocean. And when AMOC weakens, I'm using the schematic to show the anomalies of the overturning, so characterized by southward water transport in the upper ocean and the opposite direction in the deep ocean. I'm going to argue that in response to this AMOC slowdown in the Indo-Pacific, we should have an opposite overturning responses characterized by a northward volume transport in the upper ocean and opposite responses in the deeper ocean. And associated with this interbasin overturning responses in the Atlantic Ocean, we will have a southward heat transport anomaly. But in the Pacific, because we have a northward heat transport associated with warm water, we're going to have a northward heat transport anomaly in the Pacific. And because this is the heat transport in opposite directions, the residual transport into the Southern Ocean will be integrations of two, and the residual is much smaller compared to either Atlantic and the Pacific. And this interbasin overturning response is very clear if you look at climate model simulations in terms of overturning circulation stream function. So this figure took from CSM1 RCP 8.5 simulations. The top two panels shows overturning circulation stream function. We can think that as in the mean state. There's some biases in the Pacific, but anyhow, the point I want to see that in mean state, the Atlantic overturning circulation is mainly balanced in the Southern Ocean, meaning that the majority of the northern deep water come back to the surface, why Southern Ocean not falling. But when we look at the 21st century projected changes during the 21st century, which is the differences between the last 10 years versus the first 10 years of the RCP runs, we see that the Atlantic weakening, in the Atlantic there's a slowdown the overturning, but in the Pacific we have an opposite overturning circulation responses, which is in opposite sign but similar magnitude. And we talk about the transport anomaly. In the upper ocean, the Atlantic has southward transport anomaly, but in the Pacific, we have a northward transport anomaly. And in the deep ocean, it's opposite direction. So I want to emphasize that this interbasin overturn responses in the Pacific is not the the interbasin overturning of deep water seesaw as discussed in previous papers like Saenko et al. 2004. But instead, if you look at the overturning secondary street function anomalies in the Pacific, is more or less uniform gradient shows the downward vertical loss is mainly associated with adiabatic deepening isopecinals that is driven by the volume convergence into the upper oceans in the Pacific. And the dynamics for this interbasin overturning circulation responses is quite simple. And we illustrate this in serious papers using a reduced gravity model, which is kind of representation of the upper, we can think this as the upper branch of the Atlantic overturning circulation. It extends to two basins, including Atlantic and the Pacific, so it has dependence on both latitude and longitude. And the vertical has only one active layer. And we prescribe some northern deep water and have some representation for mesoscale eddies and interior diapical mixing. And in southern ocean transformations represented as some relaxation to some constant depths. And in control runs, we see that in the control run, we have the northern deep water formation balanced by southern ocean overturning, which is the balance between these two terms, and is consistent with what we think in observations and also in more comprehensive simulations. And then after reaching some steady state, we do some provisions that we reduce the northern deep formation. Because the Southern Ocean response, Southern Ocean transport is determined by a wind and also the eddy effect, which is proportional to the mean depth of the interface, which responds much longer time scales. And when we only reduce the northern deep formations, is going to lead to a convergence of volume into the upper ocean, the upper layer. And as a result, this convergence leads to deepening the interface of the upper layer or deepening isopecinals in continuous case. But because we know we have a rotation on Earth, so the deepening is its interface is not uniform. And here I'm showing the interface depth changes after like 50 years, after slowing down the northern deformation for 50 years. And we see the interface depth anomalies here. And we see some strong signatures of wave propagation. And just like the geostrophic adjustment processes, when we have the interface deepening in the North Atlantic due to the northern deep water slow down, the interface depths anomaly propagate as the coastal count waves along the red line into the Pacific western boundary as well. And after these wave processes, we establish some geostrophic transport anomalies. And if you look at the interface depth anomaly along the dashed line here, I show the interface depth anomaly along this dashed dotted line as a function of time, as indicated by different colors. Axis is the longitude. We see that as the wave propagates southward, we see a deepening interface on the eastern boundary, South Atlantic, as well as the western boundaries in the Pacific. And this interface depth anomaly and associated zonal gradient corresponds to a southward transport anomaly in the upper Atlantic Ocean, but northward transport anomalies in the Pacific. Just like this explains why we have a compensating overturning responses between the two basins, just like a geostrophic adjustment process. So now we talk about, so now we talk about why we care about this, right? We use MGCM simulations to do some simulation in very idealized geometry, and we show we weaken the northern deformation. We talk about the upper 1 kilometer volume transport across 30 south, and consistent with what we see a southward transport anomaly in the Atlantic, associated with slow down AMOC, but in the Pacific had northward warming transport. And these two compensate each other substantially, leads to a very weak response in the global. And indeed, associated with this warming transport, we also see a compensating heat transport response between Atlantic and the Pacific. The blue line shows the heat transport response in Atlantic, green line for Indo-Pacific. And the two adding together leads to a very small response, heat transport in the global into the Southern Ocean. And this northward heat transport, after following slow down the AMOC into the Indo-Pacific, leads to a convergence heat transport or heat content to the Indo-Pacific and cause the subsurface warming on centennial timescales. And this is kind of something different from previous studies that always usually emphasize vertical diffusion in diffusing the heat downward. And also I want to see that this is providing an important heat source for future Indo-Pacific warming centennial timescales. And some implications, we think this is providing an update to bipolar seesaw. It's that traditionally we think this is a bipolar seesaw, interacting between Southern Ocean and Atlantic, but we think what happens really is actually interbasin seesaw, thermal interbasin seesaw. It's like when AMOC slows down the southward heat transport and associated with, in response to this, there will be a northward heat transport. And the heat reservoir is actually in the Pacific instead in the Southern Ocean. And due to this compensating heat transport anomaly, the heat transport anomaly into the Southern Ocean is small and accounting for why Antarctic temperature changes showing more gradual changes compared to North Atlantic. So due to the time restrictions, I'm going to briefly talk about the nutrients. So this is a section of Atlantic and in Pacific nitrate distribution. And associated with the slowdowns, the AMOCs are going to decrease the supply of nutrients from Southern Ocean to the Atlantic Ocean and decrease the nutrients concentration in the upper ocean. And in the Pacific, and associated with the deepening isopecanals, they're also going to cause a decrease in nutrients as well. And when we talk about Southern Ocean, because the vertical gradient between the vertical gradient to nutrients between Atlantic and in the Pacific is such different, the compensating overturning is going to lead to a residual net nutrients transport into the Southern Ocean. And as such, it's going to cause the redistribution of nutrients around the globe associated with the interbasin overturning circulation and leads to like a change in primary production in the basins on centennial timescales. And then I will stop here and show this summary slide showing that arguing that strength in basin overturn responses to AMOC changes will play a key role in redistributing heat and nutrients when AMOC changes. And thanks for your attention, and I'll be happy to answer any questions.
Thank you very much. We have time for questions.
This is Gökhan Danabaşoğlu from NCAR. Is the mechanism that you described for the Pacific overturning circulation, can it maintain the enhanced circulation within the Pacific without any implications or anything associated with any kind of deep water formation in the northern North Pacific?
Yes, there's no deep water formation in the Pacific. You can look at this simulation. So we can see this is the overturning anomalies, right? This is the changes anomalies. We can see that this is if you calculate meridional gradients, it's kind of uniform and see no signs of deep water. So this is just mostly an adiabatic process causing balance by deepening isopecanals and no deep water formation there.
And it's mostly confined to actually south of the equator, so it's not exactly compensation. Anything that's happening seems to be happening really south.
Yeah, so that's why, right? It's, beyond the time scale for Ross wave and Calvin wave, propagation, the isopecanal in the Pacific must deepen or shallow at approximate same rate. That means to first order, we can assume the vertical velocity responses to be constant. So the overturning response is essentially integration of this vertical velocity anomaly from the southern boundary northward, or from the northern boundary southward. That's why it's concentrated to the southern boundary. This is only if you look at circulation stream functions, it's really concentrated to the southern boundary. That's why I'm arguing this is a compensation and when I plot the overturning transport, it's like only plot the transport cross Gaussian boundary. But look at the vertical velocity anomaly. That's a global. That's a basin scale responses.
Thank you.
Yeah. Thanks for the question.
It looks like we have another question online.
Yeah.
I think Alexei Fedorov had his hand up first. Alexei, do you want to unmute?
Yes, Alexei Fedorov.
Hi.
I think I have related questions, and actually two questions. One question, so this warming of the Pacific, in the Pacific, it doesn't appear to affect the surface, sea surface temperatures.
Mm-hmm.
And the second question, I understand this Rossby Kelvin wave dynamics, but the Pacific is a huge basin, so the question of time scales is still an important one. So I assume if AMOC is changing like on decadal time scales, you probably won't see the signal. If you're going to centennial time scales, you'll probably see the signal. Could you comment on this?
Yeah, absolutely. So in this simulation I show here, it's indeed because I use the ocean-only simulation, so the atmosphere is not changing. So in response to this heat conversion in the Pacific, it's like a warming the subsurface, and they're actually losing heat through the air-sea interactions. We look at a couple simulations. It really depends on the time scale, as you commented on. So we look at CO2 quadrupling experiment, and in the Pacific, it's kind of on fast time scale, on decadal time scale, there's a very fast decadal warming that's mainly in the surface mix layer, and which could also diffuse heat into the subsurface, as you said. And we did some decomposition into that, and we argued that this process is mainly occurring, like mainly being important on centennial timescales, like the slow warming processes after the fast surface mixed layer warming. And your previous question, yes, so the timescale matters, but the point is that this volume transport anomaly, as I show here, is mainly geostrophic processes. It's determined by the boundary, isopycnal, on the western boundary is the eastern boundary. And these boundary processes, the isopycnal on the boundaries is really acting fast established after the wave processes. And the mean interface depths, or the mean isopycnal depths, responds on much longer time scales, as you mentioned. That's why the Southern Ocean responds very slowly as compared to the basin Atlantic or in the Pacific transport.
Thank you.
Mm-hmm. Thanks.
We actually have one more question online.
Yes.
Thomas Hain, do you want to unmute?
Yeah. Hi, Tom Hain from Johns Hopkins. Thanks for that interesting talk. My question was about the effect of the nutrient redistribution on primary productivity and the net effect on drawing down atmospheric PCO2.
Yeah. Is that a comment or question?
Well, it's an interesting thing to think about.
Yes.
What do you think the sign of this change would be, and what's the kind of magnitude that you might have?
It's a very good question. So it's complicated if you talk about the carbons. First of all, it's like, we focus on, say, in the Pacific Basin, we draw down the nutrients concentrations upper layer, right? Limiting the prime production, such as reducing the biological bump, weakening the biological bump. But on the other hand, we are also deepening the carbon-rich water, like deep water, from being mixed to the upper surface. And also that effect is kind of reducing the carbon release from the deep ocean to the surface. So it's like there are two compensating effects there. And we do look at the carbon fluxes, and we see such a compensating effect, such as the equatorial region. We do see that the carbon flux reduces, right? It's because we are more with the carbon-rich deep water. But in the other regions, such as the mid-latitude, the biological bump is a pump like play a bigger role, such as draw more carbon into the deep ocean. So such processes. Yeah, so the residual process or net process in the carbon cycle, it's an interesting question, but I don't have a certain answer.
Thank you.
Thanks.
Okay. I think it's time to transition to the larger conversation. And really we want to be thinking about moving forward and what we know versus what we don't know. So we wanted to open the floor to thoughts on that question. What do we know? What do we don't know? And how do we get there? Dan?
Thanks. Actually, I just had a question for Wan Yi.
Okay, yeah.
Sorry if I asked you that.
Yep.
Yes, I thought it was a really neat result when you were discussing sort of the high latitude regions of deep water formation, if I understood, as a way of kind of preserving signals as they're transmitted quickly to benthic core sites where we have maybe more reliable records. And I was wondering if you could comment on the potential for other places. I know this preservation in the Southern Ocean is a big issue, but where we might be able to get like benthic records of surface processes.
Oh, okay. I guess one problem is, can we find those rapidly accumulated sediment cores in other places? I know David's student, they're also generating another several deeper cores in around the northwest Atlantic Ocean, and their results are a bit different from ours. And I guess there's probably different mechanisms explaining where the timing and the amplitude of those signals preserved in the benthic forams. Yeah, okay.
Thanks.
Okay, anyone want to comment on the things we know well, don't know well, things we really want to know?
Do we have someone online?
It's just a comment from Renellis.
Oh, Renellis?
So I was just curious, in 100+ years from now, we'll have more overlap between new paleo records and past ocean observations. And so what's the important thing to make sure we're preserving and archiving in our ocean observations for those comparisons in the future?
Besides everything, as much as possible.
All that hydrographic data that Tom Rossby just worked up, that's key.
Thank you.
I have a question. It might be naive, but I've never really thought about it until now. Is there evidence in the paleo record for any deep convection in the Pacific? And if there isn't, is that surprising with the Atlantic and turning on and off and glaciation, deglaciation? Is the Pacific always stable to deep convection? The atmosphere must be drastically different, right? So can we learn anything about the kind of stability of the present day global MOC from paleo records in the Pacific?
There's definitely people who work on that. So does anyone in the room want to speak to that? Oh, or virtual? Alexi?
Yes, well, we have evidence for Pacific deep water formation for the Pliocene. And actually, it's both modeling evidence and observational evidence for something like 3 to 4 million years ago. Presumably, the configuration of continents were more or less similar to today's, but it was warmer climate, depending where you consider 3, 4, 5 degrees Celsius warmer climate. And there was evidence of deep water formation in the Pacific and perhaps with a PMOC, with changes in sediments, changes in productivity in the high latitudes, subarctic North Pacific. It probably was not as deep as AMOC, at least in the model sense. We're talking about 2,000 meters, maybe 2,500 meters. And I also know that there is some evidence for more recent times, but I think some other people should comment on that. And one more comment on this. And apparently it was at the same time. So PMOC and AMOC were both together at the same time during the Pliocene. So at least not the entire Pliocene record, but at least the periods during the Pliocene.
I was just, this is Sophie Hines. I haven't worked on this myself, but I know that there are folks who think that there was deep water formation in the Pacific during the deglaciation and potentially like during the last glacial period. So there's also evidence from more recent times.
There was a very recent paper in the last year or two.
This is Lloyd Kegwin. Sophie, what are those? What evidence is that?
The stuff I'm most familiar with is from James Ray, but I know he's used radiocarbon and I believe there's other stable isotope evidence as well, but there are a few papers that he has from looking at this.
So I did a synthesis of the available data, or actually data that were mine from the far northwest Pacific in the Emperor Seamounts and the Okhotsk Sea, and this was an old bit of work published in 1988, I think. But I concluded that what I saw happening was enhanced North Pacific Intermediate water associated with the Okhotsk Sea. However, there's a big sediment body up there on the eastern flank of the Emperor Seamount chain, and it's presently the best parts of that are inaccessible to us today because when I went up there on both Russian ships and American ships, we weren't looking at a 200 nautical mile exclusive economic zone. And now all the really best sites to talk about this would be close to Kamchatka, which is, of course, a very sensitive thing to the Russians, and south of the Komandorsky Islands on near Meiji Seamount, which is buried by this sediment body, and also the southern end of Shirshov Ridge in the Bering Sea is really interesting. So you have a very deep channel between the northern Emperor Seamounts and Kamchatka. It's at least 4,000 meters deep, I think. So there may be waters that are dense waters that were produced in the Bering Sea that could have flowed to the east and then through this channel, helping explain what looks like a sediment drift there. And I used to talk a lot with Bruce Warren about this because there is somebody, I think Peter Lonsdale at Scripps has a current meter record up there, and it's never been published. And unfortunately, Bruce never got access to it. So, if we could only get up there, I think we could really answer these questions. And the thought of even 5 years ago, before the nastiness happening today was even a nightmare. I talked with my friends at the Pacific Oceanological Institute, and the feedback I got was that the political climate we had in the early 1990s and late 1980s is just never going to allow us. The present situation is just going to prevent us from getting up there, and there are really no paleoceanographers in Russia. So, even if I was told that we could go up on a Russian ship, this was maybe 5 years ago, and what we would want to do would be piston coring to get really long records, and it would mean designing a system to fit on their ship and then shipping it from the U.S., giving it to them, and all kinds of other hidden costs. Like, you know, I had a project with them, and then they told me they wanted $30,000 to fuel the ship. So I smuggled the money in and paid in cash. Anyway, lots of sea stories here. Thank you.
Welcome to field geology.
Okay, so I had a second question there. Can we learn anything from that, from the Paleo record, on the stability of the current global AMOC?
Feng, yeah, you have a question. Yeah, can someone get a?
Yes. Yeah, that's basically, we don't have any modern climate change, you know, AMOC change record. So the only record we have is, you know, Greenland ice core that show the clearly DO events. And we don't know what's the reason for that. Mostly it's AMOC, but we don't know what's called an AMOC change, not fresh water from at all. Yeah, so the evidence there, and because we shut down AMOC, slow down AMOC in the climate model by freshing it, actually that make us not able to simulate abrupt AMOC change.
I see Alexei Fedorov has had his hand up for a while. I want to ask if that's a latent hand or if that has been waiting patiently.
It was a late hand, but I actually have a question to Paleo people. So something I was trying to understand today. So, and it's related to Holocene. So the Holocene, about 8,000 years, it was relatively warm, and then we have a gradual cooling trend towards the 20th century. Can we actually say for sure that AMOC during this time was steady, it was strengthening, or it was declining? I was trying to get this from talks today, but there were so many different slides and I couldn't. So this Holocene period, can we say anything about this AMOC? Steady, declining, or increasing?
Okay, so that sort of leads us into that whole question, which we knew would come. What do people think?
Hi, Alexi. David Thornelli, UCL. I guess in response to your specific question, I think a number of the records that have come out, some that I showed today, but Paola also showed the new high-resolution prototyping thorium record that Jörg Lippold's been developing. And then obviously there's also Florida Straits records that are potentially related to AMOC. Most of those, I think we would say, are showing minimal change through the Holocene from 8,000 years, at least up to pre-industrial. And then we have the debate about what's been going on since or during the industrial era. I mean, I guess the other part of your question that's still debated is whether 8,000 years ago it was indeed warmer and there's been cooling since 8,000, or whereas some of the work that Feng's been part of, the climate models generally show you've had warming since 8,000 years. And obviously that then depends on how we're treating the proxy evidence. There was the recent Bova paper that you might be aware of that argued most of those previous reconstructions suggesting cooling since 8,000 years are an artifact of seasonal biases in the proxies. So there's still this big ongoing debate about what global climate has done, let alone AMOC. But I think our current understanding is probably that AMOC's been relatively steady. I think hopefully that's a fair reflection.
So Dana and Ryan, you had your hand up a while ago. Did you want to bring up something?
Sure. Well, I can return to your original questions about what we know and what we don't. Sorry, Dan Amrine from NCAR. You know, it's been a lot of fun in the Paleo task team having some of these conversations. I think what we can say, you know, things that we definitely know are that you know, paleoclimate intervals show really big changes. You know, that are really interesting, and also this is where we need to go if we're going to look at internal variability on timescales longer than the observational record. In terms of thinking about how we can translate these lessons to things of utility to physical oceanographers, and certainly that should be a two-way conversation. Already we're seeing clearly that past climate intervals are challenging our imagination about what the physical oceanography should look like. So I think that's great. But in terms of thinking about internal variability, I think we should challenge the community to think about the things that we don't know, which is, we don't have direct observations of nearly any physical oceanographic quantities, right? There's no Cibicidoides OSNAP, although that would be amazing. So there's this one challenge of translating what's in the mud to what we think about in the ocean. And then there's a second challenge of translating that into global phenomena, right, which is a lot of the conversations that we're having here. So I think we're in a position now to kind of quantify what those uncertainties are and what we don't know. And so I think a great service and a way that we should think about moving forward is to provide ambitious reconstructions of the entire ocean, not necessarily just single, local indices and stuff like that. Provide these products with error bars that we feel comfortable with, and then allow the communities to evaluate what hypotheses about physical oceanography we can test, given the uncertainties that we have in these reconstructions. So I think that's an exciting, possible way to move forward.
I'll jump in if I can. So I agree with both what David said and also what Dan is saying, and I think we're starting to move as a community to really look at the common era AMOC variability. And the signal is small for sure, but it's really important to know what that signal is and distinguish it from the noise, because humanity kind of depends on us knowing this. This is probably one of the hardest, most important questions or grand challenges to address. So sure, the signal was really large during deglaciation and through the falling Allarang warming, younger dryas cooling. We can see that, and it's tethered. The system's tethered on those timescales. And we're seeing at the observational scale, the system is not very well tethered, but we know probably on longer timescales it is tethered. But there's, we have the problem of we're studying some component or some component that is associated or could be impacted by AMOC variability, but is not necessarily in the core of it, although we saw some records by David where those are in, parts of the core, although the return flow, of course, as we know, is really complex, right? But I think, one of the things that we need to do is to somehow, as Dan said, work together to figure out this grand challenge. Because, I have to say, and this is not a criticism, but we saw data covering 15 years, and people were talking about regime shifts in the AMOC. And I'm sitting there going, but the AMOC is changing on centennial, millennial timescales as well, right? So we need this long-term context. We need to get it right so that we can contextualize the very short rapid series, the very short OSNAP series. We need your help, but we also think we have something to offer to contextualize the current situation. So that sort of goes to one of our grand challenges, is that the workshop that was held in Boulder was to really bring together modern day observational oceanographers with the Paleo people, and this really hadn't been done before. And so how do we keep that momentum? Do you still want to play with us? And then I'll just stop there and see if people want to jump on.
Chris Little's been waiting for a while, and then we'll
yeah, I'll jump in. You look like nice people, so we can all get along. So I think this question's a little more narrowly focused, and it might be something that just I don't know rather than we don't know. But it looked like in Paola's presentations that the upper branch, we could see variability over the past 1,000 years, Atlantic water, whatever you want to call it, but less variability in the last millennium in the lower branch. Did we know why? Did she allude to those lower pathways or deep water pathways? Is it because of where we're sampling, or is there a detachment between those two elements of the circulation?
Is Paola still here?
Paola's put her hand up, so
okay.
Paola, do you want to?
We'll let her answer.
Okay. Okay, yeah, no, that's a good question. And so I think this brings us back to something that David and I were both alluding to in our presentations, and is that we see signals in the surface and we see signals in the deep, but somehow they're not often related. And this brings us to trying to look at these two systems slightly separately. What we think is that the gyre, so you can shift the surface ocean currents by some of these forcings from bringing fresh water into the North Atlantic, or other mechanisms such as atmospheric forcing. And that potentially would be enough to explain centennial climate variability. We don't, however, get a coherent signal in the deep. And the records I showed are a bit bitty in the way that they sit in the pathway of some of these deep flows. And we're probably confident that these flows haven't migrated upwards. But it's true that perhaps we need more of them. In David's case, actually, I think he's got quite a robust set of data sets there, so he can probably be more confident about that. But I do think that perhaps this surface signal is not reaching the deep, and so it's something that is more constrained to the surface as opposed to the deep. I'm not sure if that answers your question.
Chris Little was nodding, just in case you didn't hear.
Right,
You
thank you.
didn't see it. Let's see, John Robson, you want to unmute?
Hi everyone, can you hear me all right? Good. Yeah, I just wanted to add, just listening to that comment about bringing together the paleo and the physical oceanographers, the observationists. I think, a key thing for me is to not leave behind the contemporary climate modelers or ocean modelers. And I guess one of the things, so the time series that David in particular was showing, but also others as well. But it is kind of scary, those very large changes that we've seen in well, I was going to say recent years, but recent centuries. And I'm pretty sure, essentially you don't see that variability really either naturally or forced, or it's very unlikely in coupled climate models, for example. And one interpretation of those changes is that coupled climate models are just nowhere near sensitive enough to the kind of forcing that we've seen. And that's obviously really worrying, in terms of thinking about tipping points. And the other question or the other interpretation is maybe it's all internal variability, and the climate models don't simulate that level of internal variability at all. And so, we really need to kind of bring all of our tools together. So it's not just the observations in the paleo and the paleo modelers. And of course, the paleo modelers, I really loved seeing had CM3 earlier. So that was great. We really need to bring all of these people together and use all of our tools possible to understand what's going on, because we're really kind of running out of time to really make useful predictions about the next couple of decades, and that's kind of what worries me. So yeah, I'm all for bringing everyone together, if possible, in the ways that we can. So that's all I was going to say.
We've got a comment in the back. Microphone's getting there.
Hi, this is Ali Siddiqui from Hopkins. I just have a quick comment, and probably taking this on a tangent now. How much of the paleo AMOC do we understand now better from conceptual simple models? And this is a question to everybody, because I think, starting out with the Stommel conceptual model, most of us learn about the biostability of the AMOC from that. And I'm just wondering, referring back to Feng's question and the answer that he's looking for, can we have some, answers to paleo AMOC variability from this more advanced, maybe conceptual models?
Thoughts on that? Feng?
Feng from University of Wisconsin. At the end of paper, we wrote we need to study alternative mechanism of AMOC changes in the climate of the past warming period, and incorporate those mechanisms into the climate model. However, we have to first stop the oversensitivity of, the AMOC to the freshwater forcing in the model first. That will basically overwhelm all the other mechanisms.
This is Chris Little again. Just following up on that, though, I mean, from my understanding of the drivers of the AMOC downturn in the 21st century, most of that is derived from the heat flux, as I understand it. We use the freshwater forcing to do these sensitivity experiments, and I'm not exactly clear why that is, but other people would know. But the heat fluxes do play a role in the AMOC downturn in the 21st century, and maybe could be involved in some way in the Paleo record.
That's a really good point, Chris. That's also my thinking, that the slowdown of the AMOC in projections is mostly temperature driven, and we like to think of the AMOC as being very sensitive to freshwater fluxes, and also one critical element is that the salt advection feedback is positive and the heat advection feedback is negative, so that tends to stabilize it. So AMOC response to warming can be thought as being more gradual than whatever would happen if the freshwater forcing would take over, basically. That's maybe an important distinction also then in when looking at analogs in paleo climate. Well, what would be an analog in paleo climate that would mimic AMOC slowdown or AMOC collapse in response to warming rather than to freshwater forcing?
Yeah, the idea of fresh water versus heat flux driving, the AMOC decline in CO2 scenario. The iconic paper is Jonathan Gregory, 2005 something. So he populated that idea that, it's a wonderful idea, that heat flux is more important. However, the experiment he's running is heat flux alone experiment versus freshwater alone experiment. But in his heat flux alone experiment, the wonderful sea ice is melting, and that actually add fresh water in their experiment. So it's not very clean. So I think if we really care about this problem, heat flux versus freshwater flux, we have so many other things to do, okay? If you really are interested, do the experiment, Gokhan, please. Just don't let the sea ice melt when your ocean warms. That's a much better experiment to compare.
All right, I'm wondering if we can jump over to a slightly different topic, and I'm going to pose this thought. So what are our blind spots being so North Atlantic focused? The question is, what are our blind spots being so North Atlantic focused? Most of the records we're seeing are in the northern North Atlantic, and we know that this system's all tethered over the entire MOC. I know this is AMOC, the A means Atlantic, but do we have blinders on? And if so, what might be the result of that?
We have Paola had her hand raised.
Yeah, I'm not, but then, I put my hand up because I thought I could answer the question, but then I wasn't sure what the question was asking.
Well, what were your thoughts? They weren't directly related.
Can you repeat that again?
Okay, I guess it's a bad question. So, what don't we know? Because we're primarily looking in the northern North Atlantic about MOC or AMOC. Right. We're very biased by our records and even our modeling I mean, I'm not a modeler, and I know people are modeling in the Southern Hemisphere, but what we've seen this week is very Northern Hemisphere focused.
Yeah, I don't have an answer to that. Someone else. Sorry.
And we'll come back to you, Dave.
This is Sophie Hines. I guess I see in the chat someone says more South Atlantic observations. I mean, I think that like trying to understand changes in the South Atlantic and the Southern Ocean is super important. Especially, I'm thinking of the stuff that Shantong showed about connections between the Atlantic and the Pacific. I think from the paleo side, it can be really challenging because it can be hard to find good sediment records in the Southern Ocean. Just there's not the same quality of records sometimes. It can be a lot more challenging to construct age models. So there are a lot of kind of technical reasons why some of those records are hard to come by. And it's a real shame because it's such an important place from the physical oceanography side and understanding some of these dynamics. And so I think, you know, that's something that trying to connect between the physical oceanography and the paleoceanography, there's some really cool mechanisms that are being proposed and suggested by some of the models. And I think, you know, one of the challenges as a paleoceanographer and someone generating records is how do we find places where the sediments are good enough to allow us to resolve these timescales and actually figure out what's happening. So I think it's a tough problem just because, you know, the mud isn't always there or the forams aren't always there, and it's kind of hard to get around that.
I'm suddenly wondering if there are large clams on small islands isolated in the Southern Ocean.
Hopefully. Okay. No?
Hi, David Sonali, UCL. Yeah, I mean, I guess another area, it's still a bit Atlantic-y, but I guess the Arctic's another potentially important place, depending on the importance of fresh water and whether it is going to cause AMOC weakening or not. But that's obviously going to be a very difficult place to get good records. I know Lloyd's been doing a lot of work trying to work up there, obviously thinking about the through flow from the Pacific, as well as these ideas about switching of freshwater routing between Fram Strait and the Canadian archipelago. So maybe that's another place that we need to focus on trying to get good records. Maybe there's some clams up there for you too, you know, want to avoid the sun.
Yeah, so for those of you online that may not have come through, so the suggestion was looking at the Arctic. So Renelli's had her hand up online. Oh, I'm talking past the mic. I'm looking at the wrong mic. Sorry. Yeah, Renelli's.
Yeah, I put down my hand because I think you said it. I was just wondering if there were many banded archives shells in the South Atlantic and Southern Ocean. That's what I was curious about.
Yeah, I mean, I've seen a couple of published reports. They're definitely in the coastal waters and maybe not that long-lived, but I mean, it's an area that's being explored.
Is it actually being explored?
By some, yes.
Yeah, because I don't go beach walking down there.
I was just going to say there's also some deep sea coral records from, I'm biased, but yeah, there are some records from the Drake Passage, from Tasmania, but not tons.
Okay, we're going to jump subjects.
Coming back to maybe I'm going to ask a very naive question here. Based on what we have seen this morning and based on the sort of AMOC declining or what's happening right now, and after the discussion that we had, I'm still a bit confused. Based on what's shown today here, and if we compare the paleo records or present observational records to paleo records, can we confidently still say, that's why I'm asking this naive question, can we still confidently say that what we are seeing in AMOC behavior today, whether declining or maybe increasing or staying steady, is distinctly different than what was seen in paleo records And can it be distinctly attributed to anthropogenic impacts?
Yeah, I think the answer is not yet. And I think that we saw the state of the art in a sense this morning with David's talk and Paola's talk, and you know, weaving it all together in one coherent way with uncertainty estimates is what we're trying to work on. And yeah, I mean, some of these elements are pointing to maybe an unprecedented change for some other aspects of the system. Maybe, you know, the data that Tom showed earlier in the week showed this pretty steady northward flow, right? And again, it's the time scales at which it's all tethered, I think, is a really important problem that we're facing. So I don't think we can confidently say one way or the other. There's a lot of conflicting evidence, but you know, we are worried about what's going to happen. So of course we're trying. This is our grand challenge of trying to answer that question.
Maybe criticism of the AMOC community in a sense. Are we too, in that case, sort of rushing to write papers that say AMOC is collapsing and all that stuff that generates a lot of publicity, and then it's really difficult to sort of counter that impact? And I mean, I know that when last year I was asked to give a seminar to a bunch of retired people, and they're really worried. And it is because if you write an article saying that AMOC is not collapsing steady state, that's not going to be picked up by the media. Yet if somebody writes an article saying that, oh, AMOC is collapsing and weakening at this rate, then that's being picked up. And it's really, really detrimental to the community in that stage. Should we be more patient, I guess?
As Al transitions to David, there was a question online about what Al means by tethered. And you're really just talking about the coherence of AMOC at different locations.
David Thornalley again. I guess I have, unsurprisingly, a slightly different take maybe than Al. And maybe in answer to your question, I think we've got enough records to show that there's something different about today. It's then the hard question of, is it exactly AMOC? As I mean, many people have pointed this out. It's much, much easier to focus in on some of the components. And I think we can look at some of those components and say, look, there's some evidence that that is very different. When you put those bits of evidence together, some can make the case that there's weakening AMOC, others can say it's the jury's out. But I mean, if I would defend the Levka's paper a little bit, and in terms of the public outreach, maybe we've said this before, maybe we're too focused on the AMOC, and you know, we care about other things. And so I mean, this is a bit of a moral question, is it acceptable to highlight to the public that there's some important changes happening in the Atlantic? And whether it's AMOC defined in depth coordinates, density coordinates, how we think of AMOC, is it okay to simplify the message and say, there's some worrying changes happening in the Atlantic, we don't understand? Maybe that's a safer message, we could say. Obviously, it's then that extra push to say, yes, it's AMOC. We all know how difficult it is to reconstruct AMOC. So I think the balance is maybe thinking, how much do we need to ring an alarm bell that things are happening, but then offsetting that with caution that, are we confident that it's AMOC or not? I mean, we want to carry on researching it for a while.
Tom? Yeah.
Yeah. I think we need to be careful about what we mean by the AMOC. This gets back to what I've been saying several times now, that there's a subpolar AMOC and there's a Nordic Seas AMOC. And we tend to treat we're using the word rather as if it's a monolithic system, but it's not that at all. And being half Scandinavian, I like to say that, if it's the Nordic Seas, that's the big deal. It's if you slow down a few spheredrips, or 5 spheredrips to the subpolar North Atlantic, you'd have to twist my arm pretty hard to get me excited about that, compared to if you slow down the Nordic Seas branch 5 spheredrips. Tom Delworth and I talked about this a little bit yesterday, and he said that you probably shouldn't get too excited about that because the the Nordic Seas branch, okay, it's transporting a lot of heat, but the atmosphere is actually transporting a heck of a lot more heat than that. So he told me that not to get too excited about that. But is he here? Okay. Sorry about that, Tom. But and maybe Tom can comment on this. But I still maintain that we should be careful to make a distinction between the two. The subpolar AMOC and a North Atlantic AMOC, a Nordic Seas. The subpolar AMOC, we have that analog in the Pacific. It's the North Pacific Intermediate Water. It's a horizontal circulation, while the wind, and there's a vertical component even in the North Pacific component. But it's this is not variations in the Holocene. My frame of mind is still more between glacial and interglacial, I admit. But that's where the distinction.
All right, we're going to give Tom a chance to respond.
And we are at our time, so let's be mindful of that.
No, I was going to respond to what Gokhan had said earlier, and I think it's a really important point that the topic of when anyone writes a paper on AMOC collapse, it goes viral and it's all over the place, and my wife asks me about it all the time. So I think it's really important. Actually, I think it'd be a good challenge for this community to write a synthesis paper. Do we see signs of racially forced AMOC weakening now? Come together. That's a key question. I can't answer it. There are lots of different responses in the literature that get lots of press. I don't agree with a lot of those, but I would like to see a powerful statement from the AMOC community writ large. Is the AMOC declining due to greenhouse gases, and do we see it now? If the paper could come together on that with a definitive answer, I think that'd be a very valuable contribution.
Let's hold a workshop and answer that question.
Yeah, I mean, fully agreed. That's where we need to go, and it involves bringing all of the groups together. And we've started to do that. We had a great conversation yesterday, and but with that, I think we have one more question online, and then we're going to break for lunch. And this conversation will just need to continue, and it's a really important one to have.
So, John, do you want to unmute?
I just wanted to follow up again on what Gokhan was saying, and I completely agree with what Tom said. I guess, to try and keep this short, I mean, we obviously did assess in the IPCC kind of where we are. Obviously, that's already lagging behind the science by a year or two, but we were quite careful, and we gave the low confidence to kind of the idea that the AMOC has gone down. And we kind of said for the role of radiative forcing, there was almost no evidence that we could assess in that sense. I think it's important, though, if I put my Rowan Sutton hat on, to kind of, think of the idea of it's our job as scientists to assess the evidence and try and come to a consensus. And obviously, lots of people more on the activist side will complain about that, say, oh, you're too boring, you're being too careful, whatever. But the important thing is to include this kind of plausible worst case scenario. And to go back to what I was saying earlier, it could be that the AMOC has declined because of radiative forcing. Now, I don't think there's strong evidence to back that up, but we have to consider that as an option, and we have to understand if that is happening, then why our models aren't showing that. And that's the key kind of challenge as we go forward, I think.
Awesome. So thank you all for this wonderful discussion. I think there's lots of food for thought for everyone, and hopefully we'll continue the conversations through lunch and during the breakouts later. So thank you.